Good morning. Come to the subject manufacturing processes 2. The module 2 is continuing, there is a mechanics of machining, and under that we are dealing with cutting forces and power consumption in machining. The lecture number 10 today that covers dynamometers for measurement of cutting forces. It has already been told to you that why it is necessary to measure the cutting forces. So, the purpose of measurement of cutting force have already been described. Now, we are going to describe how these forces can be measured. There are different methods, indirect and direct. So, direct method is much more reliable and accurate, and that is accomplished by some devices called dynamometers, which is based on some transducers. So, what is the content of this lecture today? If you see here the specific instructional objectives or the contents of the lecture today, this lecture will enable the students to show the general principle of measurement, any measurement, general principle of any measurement, then classify and apply different transducers for converting cutting forces into suitable signal, state the design requirements. Some factors need to be essentially considered while designing the dynamometer to fulfill the purpose, and develop and use dynamometers for measuring cutting forces in some conventional machining process like turning, say drilling, milling and grinding. Now, come to the basic, the general principle of measurement, how things are measured in any measurement process. Now, the physical variable, say cutting temperature or cutting force. Now, here the cutting force is a physical variable which we like to measure, but it is neither visible nor you can grip it by your hands. Okay? So, we do not handle it directly, but we can understand the presence of force or the intensity of force by its effects. When some force acts on a cantilever beam, it undergoes bending, or some ball, then this will be deformed. Okay? So, this is how we understand the presence or the intensity of the force. For example, the wind is not visible, but from the movement of the leaves and branches of tree, we understand the presence and the intensity of the wind. Similarly, temperature is neither visible nor you can catch hold directly, but from the effects we can understand the or detect the temperature from expansion of liquid or gas or something, or bending and something like that, or EMF generated. So, the physical variables like cutting force and temperature, which cannot be directly gripped or visible, has to be converted into a suitable effect which is visible, which is detectable, which is measurable. For example, now this physical variable will be conversion into another suitable variable, and this another suitable variable may be deflection of a elastic beam or expansion of a liquid by temperature, like that. This stage of conversion of the physical variable to be measured into another suitable variable which is detectable is called transducing stage. This is stage number 1, transducing stage. So, this conversion is accomplished by some transducer or sensor. They produce some signal. This signal may be voltage or something else, okay, or current, but the signal that is normally produced by conversion of the transducers is very feeble and noisy. Therefore, this signal has to be conditioned properly, amplified and rectified and smoothened by some conditioning stages. This stage is called conditioning stage number 2, and the purpose are amplification of the signal to enlarge the signal which can be easily measured accurately, filtration from the noise if any, and stabilization if there be any instability in the signal. After that, we get the conditioned signal which can be easily measured, detected and measured, quantified. How this can be done? Suppose this conditioned signal is a voltage. Now, this voltage can be directly measured by a voltmeter, or it can be if there is any pulsation or variation. If you want to see the time dependence, then we can look into the oscilloscope, and if you want to record it, okay, then we can record it on pen recorder or strip chart recorder, and we can also do it comfortably and make use of it onward by storing it into computers or say personal computers. That is called third stage or readout stage. This is called readout stage. Now, in case of cutting force, various transducers used for measuring cutting forces. What is a transducer or sensor? It is a device or element or material which converts a physical variable into another physical variable. All right, say pressure into voltage, light into voltage, like that. The basic principles of measuring cutting forces. So it is understood that cutting force, which is the force, has to be measured from its effects. All right, and what are the possible effects suitable for measurement of cutting forces? So the basic principle of measuring cutting forces from its effects are the monitoring elastic deflection of a body caused by the force. Now here is a beam, suppose elastic beam, and then this will be subjected to a force. Due to the force, it will undergo bending or elastic deformation or deflection. Then monitoring elastic deformation. If it is not a beam or if it is a ball or say a solid body, then by deformation or strain we can measure the force, and monitoring the pressure. Because of the force can be converted into some pressure into liquid or solid, and this pressure can be measured with certain other methods. So these are the basic three principles used for measuring the cutting force based on its effects. One is elastic deflection, other one is elastic deformation like strain, other one is pressure, which can be measured directly by pressure gauge through a liquid medium or say gas medium, or through a sensor which converts pressure into some electromotive force or voltage, like that. Now first let us come to those methods which are based on measurement of deflection. Determination of cutting forces by measuring deflection, elastic deflection. The basic principle. Look at this diagram. This diagram shows that here is the job, the cross section of a rod which is undergoing machining by a turning tool. This shows the turning tool or the tool holder, which is nothing like a cantilever beam. This is like a cantilever beam subjected to a force Pz, suppose one force. Due to that, this beam, elastic beam, will undergo deflection by this amount, say delta. Now this delta deflection is visible, it can be measured, unlike the force Pz. Now this delta here is equal to, if it is a cantilever beam, is equal to Pz, the force, L cube is the length of the projection or cantilever, 3EI. What is E? E is the property of the material of the beam, that is Young's modulus of elasticity, and I is a section modulus of the plane moment of inertia. This is I, plane moment of inertia of the beam. Therefore, that means that we can measure Pz in terms of delta, provided we know the other parameters L, E, I. These have to be known. Then delta can be determined, Pz can be determined from the deflection delta. Now come to this one, mechanical device. Now the question is, how shall we measure this deflection delta? This can be measured by various methods. Mind that this delta is very small. It will be order of say fraction of millimeter. Otherwise the machining characteristics will be affected, like depth of cut will change, the diameter will change. So deflection normally is a low in the order of say fraction of millimeter. Now the question is how this delta deflection will be measured. Depending upon the method of measurement, the dynamometer varies. So mechanical dynamometer, electrical dynamometer, and so on. Say mechanical dynamometer, mechanical device. Here we can put say a dial gauge. A dial gauge. Now this dial gauge fixed on a place or a structure, and then because of the deflection delta under the action of the cutting force, the dial gauge will indicate the deflection directly. Now From the, if the direct deflection is known, then L cube 3EI are known, then we can easily determine the forces Pz. But instead of knowing all these parameters, because in case of deflection or this relation, there may be other parameters also, like fixing, condition, other things, and this cross section may also vary. So there may be other parameters also, but once the tool and tool holder are made, those remain fixed. So delta remains, the delta, whatever the situation, delta remains proportional to Pz. Now the question is the proportionality factor, the value of the proportionality has to be determined, and this is done by what is called calibration. Now see the calibration. Let us have a look into the calibration. Now suppose this is the cantilever beam. This simulates a cutting tool and will fixed here subject to a load Pz suppose, and because of that this will deflect by an amount, say delta. All right. Now what will, how shall we use it as a dynamometer? You do an experiment. This is load. You apply some known load, okay? You apply some known load, say W here, and measure the deflection by dial gauge. This is the deflection delta. You measure. Suppose for a particular W1, you get a point here. Then you change the load, get another deflection, plot it here. Then you keep on plotting, and then you get a curve like this. This is called calibration curve, all right, which will pass through 0, 0 expectedly, and it should be linear on the elastic condition. Now when you do experiment, then you measure the deflection. Suppose this is the amount of deflection. From the, if you know the deflection, then by extrapolation you can determine Pz. If the deflection is less, the force will be also proportionally less. If the deflection is large, the force will be also proportionally large. So this is how it is to be. This is called calibration. Now measuring deflection by electrical transducers. Other methods are electrical method, electronic method, then optical method. There are various methods, but I shall now discuss some of the common methods like electrical. Here, this is an example measuring deflection by electrical transducer. Is a potentiometer. This is the workpiece, and this is the cutting tool, which looks like a cantilever beam. Now this really represents the tool, tool holder, or any elastic member subject to a force. This will undergo deflection. This deflection will be transmitted. There is a L-type pointer, L-type pointer which is fixed here. This is fixed here, okay. Now this pointer, this will move across the potentiometer here. Now this potentiometer is connected to a circuitry. This is the EMF force E, and this is the resistance Ri, R. So this resistance delta R, so this delta R Y will change. Because of that, some voltage will be created, delta V, across this point and this point. Across this point and this point, some delta V will be produced. That delta V is proportional to delta Ri, this delta Ri, and delta Ri will be proportional to the amount of deflection. So the force Pz will produce proportional deflection. From proportional deflection, there will be proportional change in resistance. From the change in resistance, you get a proportional voltage. So the delta V becomes proportional to Pz. Now the value of the proportionality will be determined from the calibration. So you have to do calibration. Now this is a linear potentiometer. Now this is not that sensitive. It can be a circular pot like. Here the deflection of the tool is taken by a rack. So the rack will move in this direction, and there is a pinion. So pinion will rotate. Along with the pinion, there is a pointer which will rotate along this circular resistance, and from the change in resistance along with the deflection by the force, the resistance will change here across the pin and this point, and this delta V, the output voltage, will also proportionally change. So this delta V becomes proportional to Pz, and by calibration you can develop the relation between delta V and Pz and get it used. It can be inductive pickup, it can be capacitive pickup type. This one shows a capacitive pickup type. How does it work? This is a cutting tool. On this is fixed a plate, and there is another plate fixed at the bottom with a gap D. They filled with air or any dielectric medium. So the deflection due to the cutting force Pz will cause change in the gap D. Now because change in D, there will be change in capacitance, because capacitance C is equal to epsilon A divided by around 10 D. What is epsilon? Epsilon is the dielectric constant. What is E? Is the overlap area between the plates, and D is the gap between them. So this capacitance is inversely proportional or proportional to this gap. So with the change in gap, which this capacitance will change, and this gap will change because of the deflection of the tool caused by the force Pz. Thus the Pz force and capacitance C are directly connected. From calibration we can find out Pz from the capacitance. If we have to measure capacitance in terms of voltage again. Now let us take an example of another example, say LVDT, linearly variable differential transformer. LVDT, linearly variable differential transformer, is this one. What is it? It is comprised of two coils. So one is the core. This is the core member, a solid, say carbon steel, say cast iron, and there is a coil. The coil is a tubular. It has got two coils, say primary coil and secondary coil. Now, so this coil remains, say, fixed, and the core is connected with the tool. So therefore the core will move axially within the coil, proportional to the deflection, that is force. Now this is a null position. This is the null position. From this position, if this core moves upward or downward, say downward because of the force, some voltage will be created or generated at the secondary coil, and that voltage will be proportional to the length of travel or movement of this core within this fixed coil, and this travel of the core is proportional to the deflection of the tool, that is force Pz. Therefore the voltage that will be generated into the secondary coil of this coil due to the movement of the core will be proportional to the force Pz. Now this relation will be established finally by calibration. So by calibration we can determine the value of Pz from the voltage created or obtained in the secondary coil of the linearly variable differential transformer. But here the movement should not be very large, it should be within a limit, otherwise the sensitivity will be lost. Now the determination of cutting forces by measuring strain caused by the force. Now here is a point. Now see here, in this case this is the deflection. For easy to understand and analysis, we have shown a large deflection, but such a large deflection is not very good for the purpose of machining, because if we allow large deflection for the purpose of sensitivity of measurement, then the depth of cut with the machining action will change. That is, you see the tool point comes over here, so the diameter of the job will change. So that is, machining will be affected, the accuracy of the machine will be affected, and the depth of cut will also come down, as a feed will come down, as if the force as a whole will be changed, which is not permissible. Therefore the deflection should be as small as possible, but again if it is very small, then it will be very difficult to measure. Now really where the value of delta is very much restricted for the sake of accuracy of measurement, then instead of delta we should take another feature like a strain that will develop at the in the elastic member. Now the strain is also the strain that will take place due to stress on the cantilever beam due to the force Pz will be proportional to the force Pz. So the strain from the strain which is proportional to Pz we can measure Pz instead of delta. Therefore, where delta large value is restricted, then strain measurement is the process. Now here you can see the determination of cutting forces by measuring strain caused by the force. Now here is a cantilever beam like the cutting tool subject to the force Pz, cutting force, and so because of this force Pz some strain and stress will develop at this root. Now this is a bending moment diagram. So maximum bending moment will take place here. Maximum bending moment will take place at the root. Now here what is the purpose? Our purpose is to measure the force Pz. Now the moment, the bending moment that takes place at the root of the cantilever beam is equal to PL. What is P? P is the cutting force Pz. That is our target. L is the length which is fixed. Because of this bending moment, sigma stress will develop in this section. What is the value? M by Z. M is the bending moment and Z is the section modulus. Section modulus means that the plane moment of inertia divided by the height. Suppose this is the cross section, we take the plane moment of inertia, say I divided by the height, this one y, that is surface under consideration from the neutral plane of the beam, the distance I by y. This is called section modulus, which represents the cross section of the beam, which is fixed. Once made, it is fixed. Therefore sigma is equal to M by Z. Therefore the stress that will develop will be proportional to the moment. Bending moment is proportional to the force Pz. So the stress will be proportional to Pz. Now strain that will be taking place at the surface is equal to sigma by E. So this is proportional to force. Then due to the strain, there is a strain gauge. A metallic strain gauge, it can be semiconductor also, but normally it is metallic, a coil like or a wire or a strip which is firmly pasted on the surface of the beam where the strain has to be measured. So the strain on the surface is transmitted to the strain gauge, which is a strip or metallic strip. So the strain here will be proportional to the stress. So strain is equal to stress divided by Young's modulus of elasticity of the strain gauge. Now because of the strain, the resistance will change. Electric resistance of this conductor or the strip or this what we call strain gauge will change. How? The change in resistance delta R for a given resistance R will be proportional to the strain that will occur. So equal to the constant of proportionality multiplied by strain. So the delta R, this resistance, change in resistance is proportional to strain. And what is this constant of proportionality G? This is called gauge factor. This is a physical property of the strain gauge. Delta R by R divided by epsilon, that is called strain gauge, is a property. Now what we find from here, delta R, the change in resistance, electrical resistance in the strain gauge is proportional to strain. Strain is proportional to stress. Stress is proportional to bending moment, and bending moment is proportional to the force Pz. So ultimately, so this change in resistance in the strain gauge is proportional to the force Pz. Now, so from if we can find out the relation or the constant of proportionality between the Pz and delta R, we can easily measure Pz from the change in resistance R. Now the change in resistance R, that is also very small, it has to be measured accurately by another electrical method. How is that? Now this is the measurement of by the strain by strain gauges. Now here is a tool, say cantilever beam subject to force Pz, and because of the bending moment, stress will develop here at the root maximum, and no, at the top it will be tensile stress and the bottom it will be compressive stress. If you take the section of this beam, it will look like this. Suppose you put two gauges, these are the strain gauges. This is one strain gauge, this is another strain gauge. So these two are above the neutral point, so both of them will be in tension. So R1, resistance of the strain gauge number 1 in tension, and this is R3, that is strain gauge number 3, and that is also put under tension, and 2 at the bottom. So R4 in compression, R2 in compression. So 4 strain gauges are mounted, they are equidistant from the line of neutral axis. These 4 resistance, these are basically resistance, will be connected into a Wheatstone bridge form like this, a square bridge form, R1, R2, R3, R4. Tension, compression, tension, compression. This has to be arranged in this fashion, otherwise it will not work. Now, here this circuit is connected with a potential difference E. So long R1 by R2 remains equal to R3 by R4, there will be no voltage here. This is a delta V, that is called unbalanced voltage, that will be created here. So long this ratio will be maintained, that R1 by R2, R3 by R4 will remain same, there will be no voltage. Normally the strain gauges have the same resistance, say 120 ohms, 360 ohms or 1000 ohms, these are standard. But it cannot be exactly same, so there can be slight variation. So this may not be perfectly same. In that case, to make it same, to bring it to the null condition, zero condition, some additional resistance is used for balancing. By operating this one, we make this ratio same and this voltage will be 0. Now, this will be under no load condition. Then you apply the force, known force or any force. Immediately this ratio will no longer remain same, this will change. Now this is tension, so there will be change in resistance at a compression. So here the resistance will change in a positively and negatively. Now what will be the value of the voltage? This value of the voltage delta V will be equal to GE by 4, almost equal to epsilon 1 minus epsilon 2 plus epsilon 3 minus epsilon 4. What is epsilon 1? That is the strain that will occur into the resistance R1 in the strain gauge. Epsilon 2 is in the compressive stress, and 3 this one and 4. Now since epsilon 2 and epsilon 4, these two are, this epsilon 2 and epsilon 4, the strains will take place into the strain gauges which are in compression. So they will create negative. So this will be minus and this will be also minus. This will be minus, this one and this one. So this minus E4 and minus E2, minus this will be plus. So all of them will be added. Okay, epsilon 1 plus epsilon 2 plus epsilon 3 plus epsilon 4. This will be plus because they are compressive, minus minus plus. So this will be delta V GE by 4 into 4 epsilon, alright, if all the strains are equal. So this is how here you find that this delta V, then delta V becomes proportional to epsilon, the strain. The strain here is, the strain here in any one or all of them will be proportional to the stress. Stress is proportional to the force Pz. So Pz is now connected with the delta V linearly. Now by calibration, what we do, by calibration, say this is delta V and this is say Pz, or other Pz can be put there delta V. So this will be a curve will be produced by experiment by number of known loads, and then you use for machining, and suppose you get this much delta voltage, and what is the corresponding force? This is the amount of force. So this is how it has to be calibrated first and then you use it. So this is how the strain gauge type dynamometers are used. Now measuring, there is another method, measuring cutting force based on pressure created by that force. So the first one, we understood that the force causes deflection proportionally, and from the proportional value of deflection we measure the force. Second one, from the deformation like strain we can determine the force. Third one, from pressure created by the force. Now this pressure can be created through hydraulic medium. In the hydraulic medium, suppose this is a cutting tool subject to a force, this is a hinge point, and so because of the force this will try to go in this direction, and suppose this is a piston and there is a hydraulic cylinder, okay, and so the pressure here will increase, and then you measure the pressure by a pressure gauge. So this is one method, very crude method, but it is feasible. It's a hydraulic method. Now there is another method from EMF generated by the pressure on piezoelectric crystal. Now suppose this is the piezoelectric crystal, this one, okay. This is a piezoelectric crystal. What is the property of piezoelectric crystal? If it is subjected to pressure, then some EMF will be generated at the end. So this is EMF. So this is one end of the crystal, this is another end of the crystal. They are connected to metallic plates, say copper plates, and then subject to a pressure. Because of the pressure, at the end some EMF will be generated, and this EMF is proportional to the pressure or the force that will be exerted on the crystal. Now this force can be the cutting force. So this can be connected to the cutting tool, or it can be so connected that the entire force will be transmitted onto the crystal through these copper plates. So by calibration here, so if you calibrate say force P and EMF here, and you get a curve, you apply a known force, that is known pressure, you get certain value of epsilon. Then you increase it, you get another point, keep on getting number of points, then draw a straight line or a line, that is called calibration curve. Now you put into action or cutting process, so suppose you get this much EMF, and this is the corresponding force Pz. This is how the cutting force Pz can be very precisely, accurately measured. This is a very precision method, very reliable method, robust method, but it is expensive. It has to be, and now if it is a 3D dynamometer, then it becomes more complex in manufacture. But this is a very good method, very accurate, robust, durable and stable and all these things, but problem is expensive. Now design requirements for tool force dynamometers. Now dynamometers are available in the market, so people can purchase from market and use it, but these are expensive. If not expensive, it will not, say crude method, then it will not be reliable. Those are cheaper, but accuracy will be less. If you want high accuracy, precision, reliability and consistency, then it has to be a very costly or sophisticated dynamometer, which is very expensive. However, these dynamometers need not be purchased always. This can be designed also by the users, all right. But when these dynamometers will be used, then some factors have to be kept in mind. Some factors have to essentially taken into account while designing and building the dynamometer. What are those? Sensitivity. The sensitivity should be high, so that the amount of signal that will be produced ultimately should be readable, should be substantial in amount, so that it can be read or it can be recorded. But if this this signal is very weak, then it cannot be measured. This is called sensitivity. Then on the other hand, rigidity. The dynamometer should be rigid such that it can withstand the cutting force coming into that. It should not be spoiled or broken or plastically deformed. It has got another reason, that if it is not very rigid, then the cutting tool or the components will undergo very wide deflection, which will affect the machining condition and the accuracy of measurement. So this has to be rigid. That means there should not be unnecessary large deflection. So sensitivity and rigidity are to some extent contradictory. Sensitivity demands larger signal, and rigidity demands that signal should not be too large, or say deflection or deformation should not be too large. So a good compromise has to be made through design. Cross sensitivity. Now the dynamometer is used for measuring not only one force, say vertical force Pz, then Px and Py, and for each force there is a separate Wheatstone bridge channel or a separate piezoelectric crystal. All these things are put together into the device, in a device called dynamometer. Now the cross sensitivity, it has to be low as possible. It means that the accuracy of measurement, say a particular force Px or Py, should not be affected by Pz. Otherwise, the force Pz should not affect the measurement accuracy of Px or Py, like that. So each one will be independent, one will not affect the measurement of the other. Next, stability against temperature and humidity. Now the temperature changes in the environment. Beside that, due to the cutting action, lot of heat is produced. That heat is transmitted into the tool or this transducer. Therefore, the transducer dynamometer should be such that it should not be affected much by the temperature within the range. And humidity also, it should be not affected by humidity. So proper protection has to be taken. Time response, the response should be very quick. That is, the effect force, the cause is the force and effect is the deflection and the strain, stress and etc., the voltage. This should be simultaneous, almost simultaneous. If there will be lot of gap between this response, the cause and effect, then this is a chance of error in the measurement. So time response should be very quick. Frequency response, that means the readings or the measurement values should not be, the dynamometer should be so designed and constructed that the measured values should not be affected or jeopardized or spoiled by the vibration, if there be any, into the machine. Of course, within a range of frequency and amplitude. If the vibration becomes too large, then there is no question, nothing will work, dynamometer will fail. But within a range of, large range of, or reasonably large range of frequency or vibration of the machine tool, if any, this measurement values should not be affected. This is called frequency response. Now consistency and durability. So this dynamometer should give the reading uniformly, or the relation between input and output should remain constant. That is called consistency. And durability, that dynamometer will survive longer and perform uniformly throughout its longer life. Now we shall discuss about design, construction and use of some dynamometers for conventional machining. As I told you that you can purchase some sophisticated dynamometers like say piezoelectric crystal type 3D dynamometer manufactured by Kistler company of the world, Switzerland. These are very, very expensive. Say one 3D turning dynamometer may cost around say 12 to 20 lakhs. So this is too much. So for that purpose, so this strain gauge type dynamometer or other kind of dynamometer can be manufactured and used. I shall discuss some of them. Commonly used dynamometers are, so the dynamometers can be various type as I told you, but the commonly used are: one, the strain gauge based, that is using strain gauges and connecting them. Now this strain gauge type dynamometers are simple in construction, design, manufacture, low cost but less accurate and stable. Time to time it has to be calibrated and it has to be rechecked for consistency or this relation, this soldering and connection or the strain gauge condition, resistance, etc. Whereas piezoelectric type is a very accurate, more accurate, much more accurate and robust and consistent, okay, reliable. But problem is this is expensive. As I told you, if a 3D say strain gauge type turning dynamometer costs around say 60,000 rupees or 1 lakh, one piezoelectric type 3D turning dynamometer cost around 15 lakhs. Now turning dynamometer, strain gauge type 2-dimensional dynamometer. Now here the dynamometers can be 1-dimensional, 2-dimensional or 3-dimensional. It really means if the dynamometer can measure only one force, say Pz only, then that will be called 1-dimensional. If it can measure two forces, Pz, say another force Px or Py, this will be called 2-dimensional. If it can measure all the three forces, then it will be called 3-dimensional. So far as cutting forces are concerned, particularly say turning, etc., so 2 dimensions are enough, because if we know Pz and Px, from Px we can determine Py also easily from a simple relation. But if it is oblique cutting, then possibly, and if you want a very accurate measurement, then 3D dynamometer will be required. But for orthogonal cutting, Px and Py are very simply correlated. Now here you see the dynamometer. It is constructed. It is two-dimensional strain gauge type. This is the cutting tool fitted into the tool holder. Okay, it is fixed by a bolt. The tool holder is clamped with a ring. Now this is a ring. There are two discs connected by 4 integral ribs. This is a single piece made of stainless steel. All right. This is a single piece that has got transducing element, main part, and this is the tool. That is the shank which is fitted into the tool post. It is clamped to the say tool post like that. Now this ring, now this is the force acting on that say Pz. That will be, this is the cantilever beam. So this is the length L. So this force Pz will produce a bending moment. Pz multiplied by L will create a bending moment. This moment will create stress here. So bending stress sigma, that is proportional to strain. That strain will be detected by strain gauges. Say for Pz, 2 strain gauges are here, 2 strain gauges are there, 4 strain gauges. Now you have also noted in earlier slides also that we are using 4 strain gauges. In the Wheatstone bridge, there are 4 gauges, 4 resistance. If all the 4 gauges are alive, then the sensitivity will be high. If only 2 gauges are alive and 2 gauges are dummy, then the sensitivity will be half. Then it will be called half bridge. Sometimes because of inconvenience of mounting or inaccessibility of space, we use only 2 gauges, live gauges, and 2 gauges are dummy taken from the other source, and that is called half bridge connection, and that is sensitivity is half. Sometimes we may have to go even 1 live gauge, that is called quarter bridge, or sensitivity will be 1/4. So preferably we should use always 4 strain gauges and all of them alive. So these are 2 gauges. Now this is the neutral axis, 2 at the top tension and 2 at the bottom the compression. So these 4 gauges will be now connected in a Wheatstone bridge. Say this is R1, R2, this is R3 tension, R4, and this is connected to a voltage, and this is the voltage delta V. Of course this delta V is very small. This has to be amplified, further amplified and rectified, and then read into an unit. So this part, this Wheatstone is comprised inside, and the rest of the thing are put into an instrument called strain measuring bridge, where this EMF and the connection, magnification, amplification, all these things are carried out. That is called strain measuring bridge. So this 4 strain gauges. Now this will be another force in this direction, say Px, horizontal force. Because of this horizontal force Px, the strain gauge is mounted here. This is rib, and there is another rib on the other side. So 4 gauges will be there, 2 in tension, 2 in compression. That will produce another Wheatstone bridge or channel. That is called Px channel, and these 4 gauges will produce a channel for Pz. So this is called a 2-dimensional. How does it look really? You see that this is the dynamometer, final dynamometer, is constructed. This is the front part, is the cutting tool, and this is the tool holder. This is the sensitive transducing element or transducer. That is a 2 discs connected integrally by 4 ribs. There are 4 ribs here, 1, 2, 3, 4, and then this is the tool shank, and these are the channels. So there are 8 wires, 4 makes 1 channel for Pz, another 4 for Px. They are connected to the strain measuring bridge as a readout unit, where we get finally the output in the form of voltage or some digital reading. Now this is a piezoelectric crystal type 3D turning dynamometer, piezoelectric type, 3-dimensional turning dynamometer. Here the crystals are there inside. Okay, so one crystal takes care of the force Pz, the tangential force, another crystal the Px, and another crystal Py, and all independently. All right, and this should be cross sensitivity will be as low, that is Pz will not be affected, but will not affect that Px and Py and so on. That is called cross sensitivity. So this has to be taken care of very carefully within this. So this is the dynamometer. this is the actual dynamometer, and this is manufactured by a company, world famous company called Kistler company. All right, Kistler, K-I-S-T-L-E-R, Kistler company, and this is expensive. This may be 12 lakhs to 20 lakhs. Okay, anyhow, but this works very well. Here is a cutting tool mounted on a tool holder. Tool holder is a long tool holder fitted into a tool post. Tool post is mounted on the dynamometer. So all the forces Pz, Px and Py will come onto the crystals inside, and that will produce EMF signal, and that will be taken out through this cable, and this will go to the readout unit, like say charge amplifier or say data acquisition system, or then to the personal computer and so on. So this is a sophisticated method of using 3D piezoelectric type turning dynamometers. It's a very precision type, very accurate type and robust. Now this is a drilling dynamometer. Here this is the drilling dynamometer. There are three parts. One part is at the top, this part is shown over here, and this is the transducing part, a ring like made of stainless steel, which has got, this is the boss, is central tubular piece with internal thread connected to the outer ring by 4 ribs, 1, 2, 3, 4. There are 4 ribs, okay, ribs. So this is a single piece, and that is mounted on a base. This is fixed on the table of the drilling machine by clamping. All right. Now, so this is the workpiece mounted here. This is the workpiece mounted here and fitted by this, and this now the subject to a force, say Px. Due to the force Px, axial force, this 2 ribs, all the 4 ribs will be subject to bending, and this rib and this rib, there are 4 gauges mounted, 1 here and 1 there and 2 at the bottom. So upper 2 will be under tension, and this upper 2 will be under tension, and the lower 2 will be under compression because of the force Px, thrust force. Okay. Now they will be connected in the Wheatstone bridge, and then finally into the strain measuring bridge. Now for the torque measurement, due to the torque here, these 2 ribs here will be subject to bending like this. So there will be tension here, compression there, tension here and compression there, compression, tension. So these 4 strain gauges will be connected to another Wheatstone bridge, and we produce another channel. So these 2 channels will give torque and thrust force. Now this is the milling dynamometer. Now in milling dynamometer, the workpiece is mounted on a plate. The plate is resting on 4 supports. They are called octagonal rings, and that is fixed in the base plate. That is fixed on the base, is the base plate. All right. Now here, what is octagonal ring? This is the octagonal ring, or what is called O-ring. If the O-ring or octagonal ring is fixed over here, say fixed over here, and apply a force Pz, then the stress will develop here and here. Outside tension, tension, inside compression, compression. Mount 4 strain gauges here. Say Z1, that is Pz for Pz, Z1, Z2 under tension, Z3 and Z4 under compression. Then you complete the Wheatstone bridge and measure it. For Px, so there will be tension here, tension there, and this will be compression, this will be compression. So 4 gauges X1, X2, X3, X4. When connected to the Wheatstone bridge, will give you the Px. Now 4 such rings will be put here, and this is the number 1, number 2, number 3, number 4. Now this cutting force, because of the milling, that will travel any direction. So these 4 supports will receive different amount of force. So the total force will be summation of the forces acting on this force. So the vertical force will be measured by summation of the force acting here, and this one will, that is the strain gauges here, will measure the forces in Px, and this strain gauge is mounted over here, and in this direction will measure Py. So this will measure this force Px, Py, Pz in a strain gauge type milling dynamometer. Now this is another, this is called extended O-ring. So here this is an O-ring, suppose here this is another O-ring type. Now this is connected like this. This is useful for another kind of dynamometer called grinding dynamometer. Now this is the milling dynamometer. You see that is described. This is the milling dynamometer. It has got 4 octagonal rings fixed on the bottom plate, which is mounted on the table of the milling machine, and there is a top plate which is fixed with these four rings. You see the orientation, this orientation different, and this is the job. This is the job which is mounted on the job holder. So the cutting force will be working here. They are in three directions. So one will be in this direction, one will be in this direction, another in this direction. So these strain gauges mounted on these different surfaces of this O-ring will be detecting all these forces. Now come to grinding dynamometer. This is one strain gauge type grinding dynamometer. Here you see this is an extended type dynamometer, strain gauge type. These will be two forces will be acting here. One force in this direction, that is called Ft, another force in this direction, say Fn. So two forces. Because of the force Fn, the strain gauges mounted at this point will be strained, and because of the force Ft, the strain gauges are mounted on the slant surfaces. The slant surfaces of this ring will be detecting this Ft. So this is the strain gauge type dynamometer. This is not very well, this is cheap, low cost, we can easily design and use, but not very reliable, not very accurate. For if you want very accurate measurement and study and research, then you have to go for a piezoelectric crystal type dynamometer. This is the piezoelectric crystal type dynamometer. Again, this is a crystal dynamometer, 3D, on which the job holder is mounted, on that a job is mounted, and this will be subject to the grinding process. This is the grinding wheel. So this will be traveling under the grinding wheel. So because of this, there will be two forces acting, normal to that and tangent to that on this job, okay, and that will be recorded into this, monitored by this three-dimensional piezoelectric crystal type dynamometer, and a signal EMF will be taken by this cable and put into the, say, by data acquisition system into the PC, and from the PC you get the entire information. Now this will not only give the average magnitude, if there is any pulsation or vibration, that will be also recorded. If there is any change, variation, that will be recorded. So this is very, very sophisticated method, accurate method, which has to be used, but this is very expensive. So this is how, now this is the summary, that force has to be measured, that has to be understood, and how the force has to be measured, preferably by dynamometer, and dynamometers can be strain gauge type or say piezoelectric crystal type. If one can afford, then piezoelectric crystal type dynamometers are better. If not, you can design, develop, calibrate and use strain gauge type dynamometer. Thank you.